Meeting together on January 9th, 2023, in the offices of the BBVA Foundation in Madrid, Spain, the jury has resolved to grant the BBVA Foundation Frontiers of Knowledge Award in the climate change category to Professor James Zachos and Professor Ellen Thomas for seminal contributions to the identification of a major natural event in the fossil record that provides a compelling analog for anthropogenic climate change. This event, known as the Paleo-Eocene Thermal Maximum, or PETM, took place about 56 million years ago. Zachos and Thomas convincingly demonstrated that the PETM was characterized by 5 to 6 degrees Celsius of warming and coincided with the release of massive quantities of carbon dioxide and/or methane into Earth's atmosphere, resulting in major extinction of deep-sea organisms and ocean acidification. The PETM demonstrates the implications of a major perturbation of the global carbon cycle, one similar in magnitude to what is happening today. Their analyses of marine and terrestrial records, made available through the painstaking efforts of international drilling programs, help bound Earth's surface temperature sensitivity to increases in greenhouse gases, reveals the multi-millenary timescale over which natural processes remove carbon from the atmosphere, and contextualize present-day changes with respect to the geological past. Congratulations to Professor Zachos and Thomas.
Professor Zachos, you're receiving this award together with Ellen Thomas for your role in the identification of the Paleocene thermal maximum. Could you explain what your specific contribution has been to this discovery and why it has been so important to the field of climate change science?
Well, Ellen Thomas and I were among the first people to discover the PETM, or the Paleocene-Eocene thermal maximum. And so we saw a unique opportunity to actually reconstruct aspects of the event in terms of the global climate response as well as the perturbation to the carbon cycle. Ellen and I have complementary skills. She's an expert in marine micropaleontology, and I am skilled in isotope geochemistry. And so we combined our skills to begin reconstructing details of the main features of the PETM, the scale of global warming, and the scale of the carbon cycle. We were also the first to make a connection between that global warming event and some of the major biotic responses, which had already been well documented prior to the discovery of the PETM. And so that was an important connection. It effectively brought together different communities, paleontologists with geochemists, climatologists, climate modelers. And part of the reason is that the PETM was clearly a natural greenhouse experiment, a global warming event that could serve as a case study for testing theory on climate sensitivity, on carbon cycle feedbacks. And so that was sort of the key aspect of the PETM that is relevant to thinking about the impacts of future increases in greenhouse gas levels and global warming.
What lessons can we learn from this past natural warming event, which took place 56 million years ago, in order to better understand and confront the current climate change provoked by human activity?
Well, there are probably two key aspects of the PETM that have direct relevance to thinking about future global warming and the impacts on civilization. The first is simply greenhouse climate theory and the sensitivity of Earth's temperature to changing levels of greenhouse gases, specifically carbon dioxide. And so the PETM has allowed us to derive a sensitivity of the Earth climate system to greenhouse forcing. And what we've discovered is that the theory, at least, for greenhouse warming is fairly sound. Models would suggest that the Earth's temperature would rise anywhere between 2.5 and 5 degrees centigrade with each doubling of, say, carbon dioxide. And what we have discovered with the PETM is that the Earth's sensitivity during that event was around 3.5 to 4 degrees centigrade, so at the higher end of the estimates for Earth climate sensitivity. So that's sort of one of the key contributions. The other has to do with the testing of theory on the operation of the carbon cycle and the natural processes that sequester or remove carbon from the atmosphere-ocean system. And prior to the discovery of the PETM, there were models that suggested that the natural removal of carbon from a sort of anthropogenic size perturbation would take tens of thousands of years, not centuries, not millennia, but literally tens of thousands of years. And until we discovered the PETM, we couldn't test that theory. And so with the constraints we have on the carbon cycle, the initial perturbation, the recovery, it appears that that theory is also sound, that the emissions of carbon, anthropogenic carbon to the atmosphere, the removal process will take tens of thousands of years, certainly through natural processes, to remove that carbon, to lower atmospheric CO2 levels to, say, pre-industrial. And so this is also an important contribution. Again, another way to test the theory on the carbon cycle.
The PETM provoked an extreme 5 to 6 degrees warming. Could we be heading towards such a scenario in the future if we do not reduce greenhouse emissions? And what could this signify for the future of humanity?
We could certainly generate enough greenhouse carbon to get the kind of warming that we see for the PETM, 5 degrees. And that would take a significant amount of carbon emissions. We could prevent that by reducing carbon emissions, switching to renewable energies, which we are doing in a big way now. And so there is time to actually slow the rate of rise in atmospheric CO2 levels to minimize global warming. Probably keep global warming to 2, maybe 3 degrees, but not get to the levels that we see for the PETM. And so I think there is incentive, certainly, to do what we can to try to reduce carbon emissions. The sooner the better. The longer we take, the more difficult it will be to keep carbon dioxide levels below those that would give us 4 or 5 degrees of global warming.
Are we still in time to prevent the potentially catastrophic damage of current climate change, or are certain impacts already unavoidable?
There are certain impacts that are probably unavoidable. I think we're already committed to 1 meter or 2 of sea level rise. Even if we were to reverse or reduce carbon emissions immediately. But we still have the opportunity to prevent the worst case scenarios where if we were to continue with business as usual, allow carbon emissions to continue to rise at the rates they have been for, say, the past several decades, then we're starting to talk about sea level rise on the order of 10 to 15 meters. And so I think there is an opportunity to avoid the worst case scenarios for greenhouse global warming.
Given everything you have discovered about the impacts of climate change in the Earth's past, what message would you wish to convey to global leaders about the importance and urgency of acting to stop current anthropogenic global warming?
Well, I think one of the most important aspects of the PETM that has relevance to society is the evidence for changes in the hydrologic cycle, a shift toward more intense periods of drought, interspersed with periods of wetness, heavy precipitation events. So the hydrologic cycle moves into a more variable mode. And this has potential consequences for how we plan in the future for agriculture, for dealing with issues like floods and so forth. And so as we are starting to build out infrastructure for the future, it's important to actually use the climate science to forecast for the changes in climates regionally in the process of planning. And so that would be probably the first message. The second has to do with just simply reducing carbon emissions and transitioning to renewable energies. We have the technology, we certainly have the ability to make this transition. It's more about the political will and the economics of transitioning to renewable energies and reducing carbon emissions.
In what sense can the PETM be considered an analog for the current climate change provoked by human activity? What can we learn from these extreme events of the past in order to understand and confront today's global warming?
We are talking about an episode of global warming taking place on a background climate that was already warmer than today. So this is not a perfect analog. However, what we can learn is actually what went on Earth in a period of rapid global warming in the past. We can try and model for the future, but that is modeling, it's not observation. And so there are many things changing with the emission of greenhouse gases. Global warming is just one of the effects. As we now already starting to see in our present-day world, there are many different effects. We're not just talking about a warming planet. We're looking at changes in sea level, rising sea levels. We're looking at ocean acidification. We are looking at the effects of this warming and sea level rise and ocean acidification on organisms living on land and in the oceans. And so we're seeing organisms migrating from lower latitudes to higher latitudes as the world warms. We're seeing plants migrating. Plants, of course, cannot move, but we can have seeds coming out in different latitudes as their parental trees were living. And we see, for instance, in the United States, that vegetation typical for the Gulf Coast was moving northward into Wyoming and Montana. And so what we can see actually is an example of the effects of climate change as more or less things we hadn't thought about beforehand. Things that we couldn't ask our computers to model because we didn't know the right questions to ask. As an example, for instance, we are now seeing with global warming the effects of a changing hydrological cycle. We have more evaporation and we get more and more severe precipitation, rainfall in some areas, whereas other areas get drier. And examples of that phenomenon we see in the geological record of this Paleocene-Eocene thermal maximum. Some of the examples, some of the most beautiful examples of changes in rainfall are from the Pyrenees, sections in the Pyrenees in Spain, where we see the effects of very strongly increased rates of precipitation with the result of erosion of the mountainsides and of big landslides happening at the same time. And we see events like that happening at the moment. And so we have all those different examples that are not just warming, but the effects of warming that we cannot necessarily all predict, since they are things that we don't think of. And if we look at the record of the past, then we can see all those events actually happening. And then we can ask the right kind of questions to our computer models. And so what we're having is something of an example of global warming as it actually happened, with the results on different timescales. If you think of migration of animals and plants to higher latitudes, those events happen on timescales of decades to centuries and even millennia. And so we can actually look at the effects on global warming in the past on different timescales. And that will help us predict what is going on with the very different animals and plants living today, but under comparable conditions.
What has the evidence of the PETM specifically revealed about the potential of impact of climate change on biodiversity? Could the current global warming lead to a mass extinction like the one which took place 55 million years ago?
So one of the interesting things is that 55 million years ago there was an extinction of some organisms, but it was not a severe mass extinction as the ones that have happened earlier in Earth's history, such as at the end of the Cretaceous 65 million years ago and at the end of the Permian 250 million years ago. But the data that we got from the Paleocene-Eocene thermal maximum helped us actually understand that those earlier periods of mass extinction also were linked to global warming. Before that, if you go back to ideas in the 70s and early 80s, many people thought that mass extinctions were the result of things getting colder. Somehow, as humans, we think that things getting cold is kind of bad and then you go extinct. But we now have started to realize that actually periods of global warming at different times in Earth's history have been much more severe for the different kinds of life forms than the periods of cooling have been. And we can see what it is. If you look at the ocean, we can see that the oceans are getting warmer. Oceans are getting warmer, that means that all the cold-blooded organisms that live in those oceans also get warmer. And if you are warmer, then all your internal reactions, like digesting your food, are happening faster. So if you're a cold-blooded animal and the ocean around you is getting warmer, you need more food. But of course that more food is not necessarily available. And that means that in essence you have starvation going on in the oceans. Another potential effect, and this is something that we still don't quite understand, we haven't quite reconstructed it well, and our models give us very different answers, is what the effect is on the levels of oxygen in the oceans. We and other organisms that we like all need oxygen to live and to function and to move. And for instance, the fish that we eat, or the shellfish that we eat, or the octopus that we eat, all those organisms need oxygen to live. Oxygen is much less soluble in water at higher temperatures than in lower temperatures. So we already have less oxygen to begin with in the oceans when the oceans are warmer. However, there are many competing effects on oxygen levels, such as the level of activity of organisms as well, that we need to look at if we want to predict whether the oxygen levels at specific places in the ocean are getting higher or lower. By now, for the Paleocene-Eocene thermal maximum, we have information on many localities, for instance around what presently is the Mediterranean, that oxygen levels became so low that many organisms couldn't live. And so that of course leads to loss of biodiversity in those regions where we lose oxygen levels. In addition to that, and this is very complex and one of the interesting things that people are studying at the moment also, and for which we can provide information from the geological past, is that if organisms start to migrate, their interactions with other organisms change. And you can easily see that, since if you are a plant, then you can move only slowly over generations, whereas animals can walk. And so as we see different organisms start to move to higher latitudes at different speeds, the interactions between those organisms change. And that means that whole ecological system changes. For us as humans, this is very important because in many regions of the world, populations rely on protein from fishing in the oceans. And so if the available proteins from fishing in the oceans is going to decline rapidly, then that is going to have severe effects for human beings. And we already know that at the moment, with our present levels of global warming, such organisms as corals and coral reefs are being severely affected by a combination of global warming and such things as ocean acidification. And if we look at ecosystems in the oceans at low latitudes, then we see that coral reefs are actually the builders of their own environment. And so if we affect coral reefs negatively, then the whole ecosystem, including the organisms that many people rely on to eat, are going to be adversely affected as well. And so those complex reactions by ecosystems are extremely difficult to predict. And from using the fossil record, we can get an example of the kind of interactions between organisms and ecosystems and the effect on global biodiversity that we get as the result of greenhouse gas emissions, which result in global warming and other environmental effects, including changes in the water cycle and changes in the acidity levels of the oceans.
Are you hopeful about the current measures being adopted to halt climate change in the international community? Or do you think that a lot more must be done to effectively confront the threat of global warming?
Well, as many scientists, I'm very pessimistic. That is never a good point to make. But, you know, we have been talking about this climate change for decades. And I remember that I was at a meeting a bit more than 10 years ago or so, that a number of scientists were all talking about climate change and which we were expecting. And after we all had given our talks, we were kind of sitting together and talking to each other, and we said, you know, one of the scary things of us sitting here and talking is that it sounds like all of us are actually thinking that this is worse than we actually are admitting. All of us seem to say, well, you know, let's not exaggerate, let's not, you know, be too alarmistic. But the point is that all of us seem to be actually slightly more optimistic than we really seriously think if you look at our data. And I still think that is true, as I was just saying. From what we see going on at the moment, global warming is here. We're sitting here in Connecticut, and this time of year, early January, is the time that we had snow that it was freezing every night. It is not freezing every night, and I've hardly had any snow this year. A few days ago, it was 60 degrees. That is extremely unusual. We are already seeing global warming. If you look at those strange alternations between very cold and very warm, that is typical what you expect with global warming. We had this time not that long ago that it was actually warmer in Alaska than it was in Texas. That is absolutely abnormal, and that is totally predicted from the effects of global warming at the higher latitudes in the Arctic, that we get those huge swings between cold and warm climate. In addition to that, those huge changes that we have in precipitation, where it's going to be dry and where it's going to be wet, we see that happening today. And so we cannot say, you know, we can still change everything linked to global warming. It's already here, we cannot change it. And so the question is, And for me, this is the question. The question is, how much of the further effects can we still change? And again, if you look at the past, we just have not done very much. If you even looked during the pandemic, we did not have a lot of effect at CO2 levels in the atmosphere. So we just have to do much more than we have done until the past, until actually we can start to move the dial. The things we've done in the past have not been enough to change anything in the climate as it is now changing. So we have tried to do something about the rate of change, and maybe in some years we have very slightly changed the rate of change, but it still kept warming, and it is still warming. And so some of the effects of CO2 emissions over the last centennia are still in the pipeline. We're not seeing them yet. And so whatever we do, it is still going to get warmer than today. And in my opinion, we have to really, really change the way we live if we want to prevent the world from going back to the Eocene, the period that we had no ice caps on the Antarctic. And for instance, what we see going on at the moment at the higher latitudes, those changes at the higher latitudes are exactly what we predicted, but they're happening faster than we predicted in the past. So I still don't want to sound alarmistic, which scientists didn't want to do, but I do think that we are in serious trouble, and that us humans, not for the planet, but for ourselves, we do have to change things very, very rapidly. We have to start taking action now.